me rambling. So we're going to see how this goes, because this whole presentation came out of all things, a concert. Because I play in my school band, and I had an hour's wait for a concert, and my history teacher made the mistake of asking me if I knew what time dilation was. So 3 whiteboards and an hour of lecturing later, yeah, I'm not going to do that to you. You're not going to get an hour. You're just going to get like 20 minutes of me rambling. It's going to be fun. All right, so yeah, time dilation. So just for some context, this is just a bit of history on it. So these were 4 people who were like majorly involved in it. So the first one, Joseph Larmor, he talked about how time dilation affected electrons. And so that was really the start of it. And then we had Emil Cohen, who used time dilation in relation to clocks, and he took the formulas that Larmor was using, and just instead of focusing on electrons, he focused on clocks. And clocks play a big role in the whole like theory of time dilation. Like seriously, these people don't shut up about clocks. And then of course Albert Einstein, of all things, he gets involved in everything. So this was specifically in the context of special relativity. He studied the effect of time dilation in relation to the nature of time itself, because he couldn't do anything simple. And then of course we had Herman Minkowski, and I'm going to just butcher names all night. And he introduced the concept of proper time, which serves to clarify the definition of time dilation. And proper time is defined as, in terms of 4-dimensional space, 4-dimensional space being height, length, width, and time, proper time is comparable to arc length in 3-dimensional space, arc length being the distance between 2 points along a section of a curve. The twin paradox is an example of proper time. So the twin paradox is this whole thing where you have 2 people, they're twins, and specifically identical twins. These people are the same age, they're exactly the same. You send one off into space, going really fast, and you come back, and you measure basically the age difference between the 2 of them. That is, in like really general terms, what that is. It's a little more than that. Anyway. So an important thing to note before I continue is this. Time is relative to the observer. This is very important because this entire thing doesn't work if that's not true. Because you're not, when you experience time dilation, whether it's you or an object, it's not that time is speeding up or slowing down for you. It's that you perceive everything else as speeding up or slowing down. So time moves relative to you, which is its own fun thing in physics. All right, so what exactly is time dilation and what causes it? So time dilation is the difference in elapsed time between 2 observers. So that means if you have 2 clocks, look at that, we got 2 clocks. It means if you have 2 clocks and clock A is moving faster or is further down or is further down a gravity well than clock B, then more time will have elapsed for clock A than clock B. So this is how time dilation fits into like time travel, which I'll get to at the end of this presentation, because that is the one thing that science fiction has gotten moderately right about time travel. So time dilation can be caused by one or more of 2 things. Being a difference in velocity, so that means it can be caused by either the velocity of the observer or how, so it's caused by your velocity relative to anything else. So if you shoot yourself off into space on a rocket ship and you're going really, really fast, that will cause velocity-based time dilation. Other kind is being differently situated down a gravity well, which means the further down a gravity well you are, the slower time will move for you. Yes.
What's a gravity well?
Gravity well is it's what's created by objects with a lot of mass in space. I mean, technically everything with mass has gravity, but so the Earth has a gravity well, and we are standing in its gravity well. The Sun has a gravity well. Black holes have gravity wells, so on and so forth. So the more gravity you're being influenced by, the slower time will move for you. And one important thing to note is time dilation is a direct result of the invariance in the speed of light. And that means that no matter what light will always travel at the same speed. Doesn't matter what you do, you can't speed it up, you can't slow it down. All right, so velocity time dilation. This is the first kind. In the context of special relativity, velocity time dilation means that an observer in motion perceives time moving slower than outside of their frame of reference. And frame of reference is something that's very important. Frame of reference just basically means what you see. Because, like I said, time is relative to you, so everything that is outside of your frame of reference will either move slower or faster than you. It's like everything is moving by you and you're standing still. In some cases, that is actually what's happening. So, for example, if an observer, if you have a clock within your frame of reference, and then you can see another clock outside of your frame of reference, if you're experiencing velocity-based time dilation, and specifically when you are moving faster than the other clock, you will perceive that clock, you will perceive your clock moving slower than the clock outside of your frame of reference, which sometimes is hard to wrap your head around, but I had a very handy gift for this, but it wouldn't go into my presentation, so here we are. So this essentially means that the faster you move, the slower time moves for you, and in fact, as you approach the speed of light, time begins to slow to zero. And actually, really cool thing is that light doesn't age, because if you're moving at the speed of light, time for you equals zero. No time passes for objects, which is only light. So light doesn't age at all. And an interesting thing, so we are all constantly accelerating at 1g. That's what gravity is. It's negative 9.8 meters per second squared motion, which means you're accelerating down. The thing that stops us is this thing called ground. It's very nice. It stops us from being crushed. It's great. But if you were able to travel at a constant 1g acceleration, so constantly traveling, constantly accelerating at 9.8 meters per second squared, you could travel through the entire known universe in one human lifetime. Now, this is actually impossible just because of the fact that you would go greatly in excess of the speed of light, and you can't break that speed limit, so you're kind of screwed. But as it turns out, at a constant 1g acceleration, not including braking time, so this would mean you would just like kind of hit the moon, you could get to the from Earth to the moon in 2.5 hours if you were accelerating at 9.8 meters per second. Yeah, it's longer if you actually brake and don't smash into the moon, but sometimes if you really want to prove a point, you just got to go for it. And actually, to get to Alpha Centauri, and this was a really, really fun equation to work out, really long numbers. It would take just under 3 years, but this is actually impossible because at that point, you are going much, much, much in excess of the speed of light. But you could actually do the get to the moon one if somebody wanted to try that. Any volunteers? Just want to strap yourself to a big old rocket that has way too much fuel and just go for it. I think it would be fun. If anyone wants to do that, just give me a call. All right, so the next time is gravitational time dilation. So as I said earlier, everything with mass has gravity. We all produce gravity. You just don't feel it because this is way stronger. But if you were in a vacuum and there was nothing around you, you do actually, you have a mini, mini gravity well. It's just we have really tiny mass in comparison to things like planets. So you don't really notice it. So, let's turn this page. When we stand on the Earth, we're experiencing time as normal by our standards. But if you were to stand on the Sun, whose gravity is, the acceleration due to gravity on the Sun is 274 meters per second squared, so it has a lot stronger gravity, because it keeps a bunch of planets in orbit. So it's got way more. You would experience time dilation just by standing on the Sun. Of course, you can actually do that because, star. But yeah, so the less gravity you have, the more your time will actually speed up. And this is very interesting when it comes to astronauts, but I'm going to get to that later. Really fun fact about gravity time dilation is you can see the effects of it much more drastically than you can with velocity base, just because it's way easier to change your position in a gravity well than it is to just accelerate to ridiculous speeds. According to this article that's published in the American Journal of Physics, for every 1 kilometer you're above the surface of the Earth, it adds 10 nanoseconds to your day. And I went and worked this out. If you were to spend an entire day on the top of Mount Everest, it would add about 88 nanoseconds to your day. So people who live on mountains actually, they have more time added to their day than those of us who live at sea level. Fun fact. Another cool thing is that this kind of time dilation means that the core of the Earth is 2.5 years older than the crust, because it's further down the gravity well. It's at the center of the Earth. It's kind of like how the outside of a record moves faster than the inside. Yeah, it's kind of cool. So now this kind of time dilation this is caused just by distance from core to crust. So if you were to, say, get into the gravitational well of a black hole, which I don't really recommend, but, to each his own, this would be substantial enough that you could cause, decades of time dilation just by orbiting a black hole. Really don't recommend getting that close.
So if you fell in, you would feel like you took forever.
Yeah. You'd also get spaghettified pretty fast. I doubt you'd make it very long, but if anyone wants to try it, like I said, just give me a call. I'll try and set something up. All right, so this is continuing to be important. Like I said earlier, we are all constantly falling to Earth, and this is kind of how satellites work. But that's what gravity does. It's a constant acceleration towards a point. We just, like I said, we have ground. It's very nice. It keeps us all alive. So here's where satellites come into play with time dilation, because this is really interesting, because with a satellite, you're further up a gravity well, but you're moving really, really fast. So the velocity of the International Space Station is 28,000 kilometers an hour. GPS satellite is about 14,000, and the GEOS, which means Global Earth Observing System, as it turns out, you learn something new every day, is 11,000 kilometers an hour. That's how fast these objects travel. So satellites experience time dilation, and this is actually a problem that they have to work into the internal clock of especially GPS and GEOS satellites. Right? They all have internal clocks that they use to keep sync with clocks on Earth. But you're up there long enough, and you're experiencing velocity-based time dilation. So this means that time is moving slower for all of these satellites we have in orbit. So each of them in their internal clocks, they have to compensate. Every day they have to roll their clocks back just a little bit. You barely notice it, but they do have to do it. Otherwise, it will go completely out of sync with the clocks on Earth, and that would just not be good at all. So like I said, gravity in right when you're up in orbit is a lot weaker. So it flows weaker, which means it should actually be going faster. Right, time for these satellites should be going faster, but because it's moving fast enough, it ends up going slower. So an astronaut that spends 6 months on the ISS will add 0.005, will have aged 0.005 seconds less than those of us on Earth, and that takes 6 months. Because that amount of velocity would actually cause much more substantial if it weren't for the fact that you're further up the gravity well. So if you could travel that fast, like on Earth, you would actually start to experience more substantial time dilation, where you would be aging much slower to everyone else relatively. But it's not just satellites, in orbit. That's not the only place where you can experience time dilation, within within the influence of Earth. If you were to get on a submarine and go 300 meters below sea level for 6 months, you would be 0.5 seconds younger than anyone who remained at sea level. And this is apparently something that has actually happened, according to what I found. So if you, this is what I mean, where gravitational time dilation is a lot more extreme than velocity-based. It's a lot easier to see the influences of it, because 6 months on the International Space Station and you've aged 0.005 seconds less. 6 months, 300 meters below sea level, and suddenly you've lost 2 zeros. So gravity is a lot. It has way more influence on time than velocity does. And as I said earlier, when you get with the speed of light, which is approximately 300 million meters per second, you're not experiencing the passage of time at all. So if it were possible for us to move at the speed of light and not die, you would suddenly, time would not pass for you at all, which is kind of cool. So, and that's what I mean here. The speed of light is invariable. It never changes no matter what you do because
In a vacuum.
yeah, yes, sorry, in a vacuum, and this is all about in a vacuum because but this is interesting because any light that's coming from from other stars has not aged at all. So we're seeing this light from millions of years ago because it takes that long for it to get here, but it hasn't aged at all. So the light that comes into your telescope right when you're looking at the stars is like no time has passed for it, which is like I don't know, I find this just really cool. All right, so now to the fun part about time travel. So time dilation does actually offer the possibility of time travel, and not just in the, oh, this is some theory. Like it could actually happen if we could figure out a way to get there. And by get there, I mean get to something with sufficient gravity to do it. So it is actually possible. How many of you have seen the 60s version of the movie Time Machine? Okay, so a few of you have seen it. Where he's sitting on the time machine and you see time speeding up around him, where basically he doesn't really age with time moves. That is a great example of what time travel due to time dilation would look like, right? Everything else is moving faster, and you see everything moving by you faster and faster, but nothing seems to be changing for you personally, and that's all about being in your frame of reference. Now, despite what science fiction would like to have you believe, it is not possible to reverse time. So time travel, in this sense, is a one-way ticket. You do not get to come back. So if you miss, or the future is worse, too bad, you're stuck. There is no going back. You can go forward as much as you want, but you cannot go back. So to allow for time travel to actually be noticeable, ideal situation, get into a stable orbit around a black hole and go stable and escapable. You want to be able to get away, because the whole point of going forward in time is to see the rest of the future, preferably not by being stuck around a black hole. So if you got into a stable, escapable orbit around a black hole and you were traveling fast enough, not only are you experiencing time slower than everywhere else due to your velocity, but you're also experiencing it slower in relation to everywhere else due to being much, much further down in gravity, just because of the sheer amount of gravity that a black hole produces. Although, unfortunately though, the closest black holes are thousands of light years away, so not really an attainable method of time travel. However, one possibility for a theoretical time machine would be a small capsule with the mass of Jupiter. So not too much to ask for, just a real hefty capsule. Being inside such an object time would be moving 4 times faster outside than inside. So I mean, if you could stand on Jupiter, you'd probably have a similar effect. Probably wouldn't last that long, but like most things, you could try it for a couple seconds, see what happens. A real world example of somebody who has actually experienced time dilation to a significant degree is the cosmonaut Sergei Kirkorov, and he holds the world record of 20 milliseconds of less aging. So, anti-aging tips, just go really fast. Just book it. So yeah, that is everything. So, anyone have any questions?